I'm going to start going on the lecture itself because now it's 8:38. I went a bit too long. We're going to be talking about JavaScript and D3 for the lab today. And it is frustrating, which means you need to do a little bit, test, a little bit, test. You should always do this, but programmers in general and people in general are lazy. And everyone thinks, oh, what's the worst that could happen? It can't be that bad. And so you do a little bit too much and then it bites you. At least I do. That's one of my tragic flaws. Last time around, we were looking at how we can rearrange your data, how we can deal with visual representations of data, but particularly we were looking at keys and how we organize, arrange, and sort of look at our data. The data is the same, but if I have a single primary key, tertiary key, so multiple different keys to view this, or no keys at all, I need different visualization techniques. And if I need to arrange things, let's say here is, I have a primary key which would identify, or a particular record, which is going to be indicated by one of these lines for parallel coordinates. Each one of those things is an individual record, and I have different attributes that I can actually rearrange or get them to be moved around so that fuel economy and the number of cylinders changes how good the fuel economy is, for example. And if I want to see that relationship, I just make sure that the bars are near each other so you can see how they switch around. If I want the year and how many cylinders, cars are at various years, that might be something really interesting to look at. But this parallel coordinates has pros and cons. One of those cons is that there's a lot of lines here, right? It's hard to track individual things. There's a lot of, as soon as there's any kind of crossover and you have to remove multiple layers, you're not seeing the connection. You cannot see the connection between cylinders and year if there's any correlation between the number of cylinders and what year the car was made. But there's no right answer to any visualization. We were making all these decisions. And so we were looking at the various things we can think about. Do we use, radial representation of the visualization, or do we use this parallel coordinates, or we can do rectilinear, right? So just a rectangular grid, put them in sequence. Or we can do crazy things like this, where I arrange and arrange and arrange and arrange, and I have connections between them. This is sort of this whole technique of the lineup system here. The idea is I can rearrange each one of these columns, and the columns are connected by a line, and so you sort of parallel coordinates with a rectilinear ordering up and down. And then we have one last thing, which is time series, which is one of the few times we do quantitative data as our key, essentially. That you put quantitative data here, but since it's effectively continuous, or I discretize the space, but that's one of the few times. Most of the other time it's ordinal data or categorical data as my record, as my identification, as my ID for my key. That's the word I'm looking for. All right. And we talked about divergent systems, which are a slightly special thing. We'll even look at color and why you have a divergent color scale later on, or very soon, actually. But I wanted to hit a couple terms, and then we're going to get to perception. So just you can type in here, maybe type in the chat, what's the difference between the mean, the median, and the mode? They're all the average, by the way, which is why I hate the term average. And Excel used the term average. You're like, no, it should not be the average. I keep on writing down the mean when I want to take the average, and it doesn't work. Yeah, sum divided by n, right? What's it good for? Normally normal distributions. Anything where I have, it's not even normal distribution. The distribution can come from actually the average. That's how you figure out if you have a standard deviation and the like. But it's for quantitative data, not ordinal data. The distribution, and you can still show a distribution for ordinal data, but I can't use the average. It makes no sense. If you have 3 medium t-shirts and 3 large t-shirts, what's the average size? Uh, right. It makes no sense. I can't do that in term for, I can't take the distribution. I don't have some way of measuring the centerness of medium and large t-shirts, for example. How about the median? Middle value. Great, Lindsay. All right. Middle value. I got corrected by my students on this one. So I'm very attuned to it. I've always say medium value. And it's always going to be a value in the actual data set, right? Median should always be in there, except if you have an even number of elements. If you have an even number of elements, you take the average of the two or the middle point between two of our data points. And yes, Isaac, perfect. Nice segue. It isn't as skewed by extreme values. The distributions that you use for it are also not as extreme, pulled up by extreme values, which is, I don't know how many of you looked at houses, or probably not that many of you, but anything with a big ticket item that can go really, really expensive, like wine, for example, anything where it has a low end, a whole lot of in the low end, and some extremes in the other end, they always use median, because that extreme, first of all, they don't want to scare off buyers. And number two, that extreme tail, extremely long tail to this distribution means that the median is going to be more representative of where that center point is, not someone off on the edge. So for example, your exam grades, median, although we always use the average, median is a pretty good measure here, unless we throw away a lot of data. Because literally in 1400 last term, I had students that did not log into CU Learn at all. They were registered for the class, didn't even take the final exam. Now, if everyone else is, let's, if I'm lucky, everyone else is getting 60s, 70s, and 80s and that sort of thing, and there's someone with a 0, that's an extreme thing. And that completely throws off our average. And yet the median doesn't get pushed off at all. It just shifts a tiny bit over. That's why for extreme cases, if you don't have a normal distribution, you want to use the median is a good descriptor of where that center point is. What about the mode? That's a weird one, but and now I normally have a full-blown statistics thing on this one. Most common value. Yeah, I'm counting a bunch of values. The mode is the most common one. It's really used for categorical data, and that's about it. So people tend to like the mode. It's sort of the ugly duckling of statistics. So if I'm talking about a normal distribution, in case you ever wonder what the hell the bell curve was, that's it right there. The normal distribution. It is unfortunate what everyone thinks everything is. So I keep on getting in bubbles, not the word I'm looking for, but people always say, oh, the class is normal distribution. I'm like, how do you know it's a normal distribution? Grades in a class can often be what's called bimodal. It does this and it does this. It has 2 lumps. It's like a camel, right? It's a 2 lump thing instead of a single lump thing, which is a drometer, or is it the other way around? Anyways, so this would be, this is how many A's, this is how many people got 30, 40%, 50%, 60, 70, 80, whatever the case is, right? This would be how many people are in each of these buckets. But if I drew what their grades are, or how many of these grades are, you normally get these sort of normal distribution. The Museum of Science in Boston has a great little exhibit on this, where they have just essentially a random, like almost like a plinko. A ball goes through a whole bunch of holes and it goes into a whole bunch of bins. And it's purely random. So each ball just gets fired into one of these bins and it bounces around and falls in. And by the end of the day, they just have one ball landing once every minute. And by the end of the day, you just get this beautiful normal distribution every single day, because most of the balls will end up getting approximately the center. They can go into any of the bins, but that's what you would expect to see when you get pure random chance. By the way, there are other ways of doing distributions, not just normal curves. So for example, you can count number of occurrences. This is a dot array, where every time I get a dot in this particular thing, it goes here. And on this particular value here, it goes here. So essentially, I get this curve by just putting extra dots in there. I'm not counting at all. I'm just plopping down a token for each dot that I get. Or a tally chart, which looks kind of weird. That looks kind of, this looks kind of childish. Does the job. Which is the most common one? This one right here. This big, they're all horizontal, right? And then it's the stem and leaf plot. How many times you got the number 1? 233 times. How many times do you get the number 2? This number of times. I think that's what we're doing here. I always have to look up stem and leaf plot each and every time. I know what it's for, as in it naturally gives you this distribution based on the numbers that are being shown. But yeah, so I think these are a count, and the number of digits that you end up popping down end up telling you how frequently certain things are. But for the life of me, I always forget. So it's one of those cases. I know it's going to give me a distribution or a number of occurrences without necessarily doing a count. It's just another way. There's just alternate ways of showing a distribution. A normal distribution. If I don't have a normal distribution, I need other tactics. Here's one. I used to think I was wrong about this. I fully admit to it. George Box is actually a statistician. A guy named Box that's his last name. And word around the campfire is that he invented the box plot. No, but he was the exact contemporary of someone who did invent the box plot, who we'll see very, very soon. I do believe, and you can correct me if I'm wrong, John Tukey was the person who invented the box plot. It doesn't really matter. Somebody would have come up with the idea soon enough. This is what we would use to show the distribution for or one of our ways of a nice flat space-saving way of showing a median distribution. Because I can put the median value right smack dab in the center. I can have 1/4 of the numbers go over here. This is the space for where 1/4 of the numbers go. This is the space where another 1/4 of the numbers go. Here is another 1/4. Here is another 1/4 of the distribution points. And by doing this, I get essentially effectively 100%. There still can be outliers, but 100% of my data, but I know exactly where the bulk of the stuff is. 50% of all my numbers are in this range, and my center point's clearly indicated. I can also do this, same kind of thing in the pointillization test. And I love these things, like the stripe graph or the point graph, where by just dropping down numbers a bunch of times and using a bit of transparency, I can clearly, in this case, for the transparency, in this case, I can just put another edge in there. And I get a thicker and thicker and thicker band of blackness in certain areas. And I'm not counting. This is great for ordinal data for that reason. I'm not counting. I'm seeing how sort of stripy certain areas are. And it's pretty clear where things are. They do that with COVID-19 right now. If you look at a map of the US and they'll show all the dots where sometimes you'll use a circle for it, but sometimes you just plop a dot on the map for each time there's a case or an outbreak or something like that. And you'll naturally get certain areas are redder than others because of the sheer frequency of points. So again, we can have outliers that normally we throw away, but the lower quartile, quarter of your values are here, quarter of values are here, quarter are here, quarter are here. It tells you the distribution, but it tells you where the middle point is. A little, I find it funny. I'm a nerd. XKCD to the rescue again. All right, I'm gonna move on. Hopefully you guys can read fast enough. So there's a bunch of different things we could do. So here's a box plot, a terrible box plot. If the you can do box plots and you'll get weird answers. So if I have a purely bimodal distribution and I go for the box plot, I'll get something like that. I might get something like this, and that's not ideal. Sometimes it's not the best approach in all cases. So all my points are on the outside, and because there's no overlap between them, the center point is smack dab between these two, but not actually in between these two, and there's actually nothing in my distribution. Another thing I could do is use levels of saturation, and I have little bands for how frequently something happens, and I just color it in more. And just that layer of those, just putting them one after the other and using different levels of saturation or intensity, light intensity, will give me a different data. And we'll actually look at that very, very soon. And here would be another bad, box plot. But you can do box plots in Tableau. But I'd like to point out this one. So let me give you the URL so you can play around with this thing. Yeah. I love playing around with this damn thing because you could try a whole lot of these different plots. So right now it's showing a box plot, but you can have a notch box plot. You can have a violin plot, which we're going to see in a second. The bean plot, bean plot, and the bee swarm plot are pretty cool. They're all ways of showing that distribution because people will say, oh, well, what's the median? And I go, who cares? You need to know how that data is distributed. It's not just a number. You need to see how the data looks. And that's something that I want to make sure that you guys think about when it comes to your projects is it's not just how slow your commute's going to be. You need to see that distribution because that distribution tells you everything about, or gives you a lot of the context you need to make an informed decision. If you're playing around with I still think try the bee swarm plot. I'm not going to actually show it, but you can have a look at these things. I think they're fun. But here's the problem with some of these distributions. This is actually the problem with the box plot. Here is a data set, a bunch of random data that we're programmatically shifting in a particular direction to these particular bands. Here is what the histogram looks like with a frequency of different points. How often you get this number, this number, this number, this number. So it's the histogram, how common certain points are in the x coordinate. So the points in the y coordinates aren't moving around at all, but they're shifting in the x axis. So they're moving to these high points. And here's what the box plot does. It's completely hiding what happened to the distribution. It's not normally distributed. It's not randomly distributed in this area. It is forming these little bands, and yet it's completely being overlooked by the box plot. Same thing here, same thing here. Box plot, this is the same box plot for all of these bands, A to G, same box plot. Nothing's happened, and yet radically different distributions. Every single one of those are different distributions, and all the box plots are exactly the same. And here's a violin plot. Same idea as a box plot. It gives you a distribution. It tells you how many points are in each of these spaces. The key to a violin plot is it also has its outside shape to it. So if you have a data distribution that is normally continuous data, or at least quantitative data, so some kind of nice measurement, or I have a lot of I want to figure out how it's distributed, a violin plot is a really nice way of doing it. It gives you approximately the shape of how the data looks, how it's actually distributed, without taking any more space in the box plot. So, but it's programmatically a bit harder to do, but it's something to think about if you want. You can't just, you don't want to just, I have a mean, it's good enough, right? You want to think about, do people need to see how the data is distributed to make sense of what actually happens? Because if someone just says the average is this, that means nothing. So if my average for my exam is, let's say 60%, but there's a whole lot of people that didn't even take the exam. Now they're not outliers. There's enough of them that they're not pure outliers. And you don't want to just throw it away. What you actually want to know is how it's distributed. That distribution tells you something. And I don't want to just take the average because I'm going to think it's 60%. Oh my God, my exam was too hard. And then you look at the distribution. If I removed and look at this distribution, I have the low end, it goes blip, and then I have this other band. I want to see what the other band is. The distribution tells me that. And then I can say, okay, I'm going to remove anyone that didn't do any of the assignments, for example. Remove them from the data set. Then I'll look at my average. Now the average is 70%. That's much better now. But I won't know that that's the problem until I look at the distribution, one way or the other. Histogram, violin plot, box plot. Quickly, at least, Distribution and correlations. If there's one thing my psych degree has taught me, my stats in psych has taught me, and I'm hoping to teach you, the number one rule: correlation does not equal causation. Say that again. Correlation does not equal causation. And you go, of course it doesn't. Yeah, but everyone falls for it. So specious correlations, or there's a great website on this one. You can have a look at it. For example, global warming is caused by piracy prevents global warming. Because piracy was big, global warming happened, and the rate of piracy in the world dropped off, like old-timey patch-wearing pirates. Global warming increases while piracy goes down. Therefore, piracy prevents global warming. They're correlated. There's got to be cause and effect. Okay. That's what we're talking about. One of the things we're talking about here, or overfitting the data, like this piece of garbage, right? There is no line. You put a line there, people go, there's a line, there's a correlation. No, there isn't. It's a big bunch of dots. You can try and fit a line all you want. That doesn't mean it's actually an accurate representation or the best way to fit the data. So the GDP per person is here, the property crime rate is here, and there's clearly a correlation between how much the GDP per person in each of these states and the property crime rate. No, there's not actually a relationship at all in this case. That's why you have to be able to look at your statistics. Even if it's not, we're not going to go hardcore in statistics, but if you put a bunch of dots and you put a line of best fit and it looks like a big cloud around it, I'm going to call you on it. And in case you're wondering, I already showed this, but I still love this. The mean, standard deviation, and the correlations are all the same for all of these data sets. And yet this is what the data sets look like. Sometimes you need the distribution as well. Okay. Because the descriptive statistics aren't sufficient for what you're looking at. And that's actually a big John Tukey thing. He's a big fan of look at the data, play with the data, then give you the descriptive statistics. You can't just crunch numbers and get some magic number out of it, no matter what someone says. Okay, so we looked at all those things, and this is what I was going to do this time right now. Perception and cognition. So let's take not a break, but I want to get to this as soon as I can. So yeah. Because all of this stuff, talking about statistics, all about talking about tasks, talking about visualization, all this stuff, if we don't know why it works, how do we make an informed decision? So what we're going to be talking about is why all these visualization techniques that we're going to be looking at work, why we do things a certain way. It all makes perfectly logical sense. It's just you need to know something about how anatomy works. So we talked about arranging tables and alignment of data and all this. And why do we need to do that? Well, there's a fundamental reason we're going to get to today. We looked at point distributions, right? Ordinal data. All right. We looked at point distribution we just looked at. And that's why is it that we see certain things when we, in certain cases? Why do we use a violin plot? Why do we color it that way? What fundamentally drives all of our designs? And we looked at live factors. Again, to remind you, just to show you what the data would look like, we talked about live factors. It's the image, the delta or the difference in the image between two measurements and the actual data difference between two measurements and how off that is, right? They should be the same difference for both the visual and the data. And if they're not, I have a live factor, either overstating or understating the value. And so we had things like this, but more importantly, we had things like this, which was in the homework. And how would we do this live factor? Well, one thing we could do is we could actually measure what I consider the volume of these dollar bills, right? We do know that it's meant to imply at least a rectangular volume. And you would measure the height of each of these things, you measure the area of each of those things, and you get a live factor. Great. So I have a width, I have a height, good enough. I can calculate this particular area. And so I have a live factor of 1.16, I do believe on this. If you were close enough, good enough, right? It's trying to show how much of a lie there is. How about this one though? Just the visual perception area. What hits your retina? Rather than you thinking of it as a volume, it is the amount of green pixels on the screen, essentially. How do those change? I actually have a rather wicked lie factor in this case. If I actually measure those particular areas, so make triangles at the top and the bottom, you know, the top and the bottom, and then that becomes a rectangle, that becomes two triangles, and I can get the visual representation of that stack of dollar bills. That will give me a different lie factor. It gives me a lie factor of 6.72. It's rather extreme, I think, because of this thing and this thing here. Right? Same thing here. I have one lie factor. If I say this is the size I think this cylinder is, and they're both right, by the way. This is the size I think this cylinder is. This is the size I think this cylinder is. So I calculate the 4 pi, no, not 4 pi r squared. It's just pi r squared for the area of a circle, and then multiply it by the cylinder height. Good to go. That's how I could calculate that, and I get a lie factor of negative 2.74, or and if my volume in this with the same, presuming the same size top, I get a 1.62. Okay. Or I could say actual height in terms of visible area. Do visible area versus not visible area. I can do how much of the space is actually hitting my retina. So the expected rectangle here, or just the visual rectangle here versus the amount of purple pixels here. And I can get a lie factor. It didn't matter which way you did it. You just had to be methodical in how you were taking apart this thing and saying, no, this is garbage for this reason. I'm going to measure this, and this is how much how much this is measured on the screen, whether you're calculating the volume, the implied geometry, or actually what you are actually seeing, the actual size of this image. If you did not recognize this as a cylindrical object and you just saw a purple blob, how big is the area of the purple blob, essentially? So we're not going to do it as an exercise, but I wanted to, well, think about this one. This is Robert Coursera, who's actually on my doctoral committee, surprisingly, but he just took this thing to task, but I'm not sure I did a better job than this. This is what cloud visualization, I think it's what the actual term for it is. It's supposed to look like little fluffy clouds. So essentially you have a normal you have a distribution of your data, like a histogram of your data as you go up. And what you'll see is, so this is when people do dancing at 3, 6, at 3 in the afternoon. Like what time do people do their various exercises? Oh, no, this is midnight, 3 in the morning. So this is 3 in the morning to 3 in the morning. So when does dancing occur? When does dancing occur? When do people play billiards? When do people play softball? When do people bowl? Right? And you can just see how different exercise happen. He didn't particularly like this. I'm not sure what you think of this. So I'd like to maybe have some people throw some words on in the chat for right now. What do you like or what do you not like about this? Is there something better? Would you suggest something better? Because we're trying to show when people play exercises at different times in the day. Yeah, clouds in the front block the clouds behind them. The occlusion is a problem. It's part of the design because it's trying to look like flowy clouds. But yeah, if you have something like, let me see an example. Practicing martial arts and playing a racquetball sport, sort of it's occluding something in the martial arts. If there are people playing martial arts in the morning, it's being occluded. It is surprisingly only a sometimes thing, but it is something to be aware of. Yeah, nice. We didn't even notice that one. So I like the fact that you're gonna see the workout team sports are at the end and individuals are space. Where do you see the at the end? Oh, that they're banding over on this side over here and the individual ones over here. Yeah, that is a. I thought they may have been distributing it this way, but yeah, I think that's a great point, and it's getting the point across, which is when people are playing certain sports in certain times of the day. Yep, and it's very hard to find the compare the sports at the top. I'm not sure what is the measurement. Can I compare? I'm pretty sure fishing is not more popular than all the other sports here, unless I'm really different than everyone else. I have no desire to go off and sit in a boat or sit on some ice and fish for 12 hours a day. Maybe I'm just weird that way. Just grab some random animal by the lip, just sit around, drink beer. Like it doesn't seem like it's not my cup of tea. And I'm a Newfoundlander, might I add. Right. So this is weird. I don't think they're actually on the same scale, which is something I only notice every time I've had. Oh, and hunting. Yes, because I'm sure you're all out hunting on a regular basis. So they have their own distribution. They're not actually comparable across top to bottom, other than the time of day that it happens. What other thing? I actually love the fact that it's a little blue and it looks like a cloud and it's sort of calming, and you get the general sense of certain things. Uh, there is that occlusion, but at least they're using two different blues, so you actually can separate with two different brightness and darknesses, so you can actually see the difference, which we'll get to hopefully today. Oh, and yeah, the morning peak, the evening peaks, the more evening peak ones are up here, the more morning peak ones are down here. So using cardiovascular equipment is down here. Running is down here. Everyone runs in the morning, it turns out. And playing baseball for some reason. No one plays baseball. No one plays baseball at night. That's really surprising, actually. No, vehicular touring racing is up here. Yeah, you don't want to be doing that at night. Playing soccer is later in the day. I'm really surprised. So Robert Casera tried to redesign it, so you can see what you think about the redesign. One of the big things being, if I say fishing, oh no, fishing still has a huge, like using different banding so you can actually, it doesn't go beyond a certain height so that they don't occlude from one another. And he's using an intensity to show where the most intense parts of the day are. But I would argue that the data itself is not calibrated across the board here. Uh, yeah, okay, that was already answered. Already talked about. So playing basketball, playing middle, what 5 o'clock in the day is for playing basketball. Middle of the day is for middle of the day is for, let me see, golfing. There you go. Walking is distributed throughout the entire day. I almost guarantee walking is more popular than all these other sports, and yet it doesn't look that popular. Um, I would argue, so depends on how you want to view things. They're the same data set, though. It's good to be able to think about how these things work. We do have this occlusion, but this doesn't give you the fluffy cloud view, but it does more accurately sort of compartmentalize all these parts to see exactly, and also to see exactly where that peak is without having to see just have it go way up and block other parts. I just use intensity to show that. Go darker essentially. So you get this nice banding effect. But notice that the banding effect means you go not so popular, very popular. Even it could be a gradual difference, but that change in color is not gradual, and it makes it look like it's discretized to small, medium, large. It becomes ordinal data when I do it this way. Versus this, if it's a little bit higher, it's only a little bit higher, but this would be a black band versus a darker orange band, or dark brown versus darker orange band. All right, so we're going to look at basic anatomy of vision, and I'm hoping not to overly nerd out on this one because I can. Um, I try not to because it drove me nuts when I was an undergrad. And yes, I did this as an undergrad back. So anyone that knows has had me as an instructor before, you know I'm not a big fan of memorization. This is the reason. My first degree is a biology psychology degree. I stunk at it. And maybe that's biasing me. Maybe that's you're being tortured as a result of this, because I'm always like, you'll learn that the words later, you'll learn the syntax later, meh. But the fact of the matter is, when you're programming, at least, you will learn the words later. You will learn the syntax. What I loved about it, when I hit the field, I was like, oh, it's not memorization, it's understanding. And I like that aspect, but there's a lot of terms to memorize here. You won't be asked to memorize any of these terms, um, but just still. The point I want you to take away from it is how this low-level processing affects how you view the world and how you view visualization. Because despite what some people think, I've had friends that that don't have any background in this. They think we have little cameras in our head, and that you see the world, and somehow it's all encoded like a tape recorder, and it's just a matter of time. You do hypnotic suggestions or something like that, and you'll get a perfect reproduction of the world that you see. And the world is not accurate. In fact, the world is I missed the slide I put in for my grad course. The world is constructed. Your world is constructed. You cannot assume what the other person sees because their world is constructed. It's one of the weird truisms of the world, that what we see in the world, what we think of as the world, is not actually the world. It is your interpretation of the world. And as a result, it means that you can't make, you're trying, as a designer, you're trying to design for someone where you do not know what their visual perception is. You do not know how their interpretation is going to go. You do not know how they're going to use that particular system. But if you know how most people see, you can make educated guesses. So let's get going on this one. So this is your eye. It is effectively like a camera, like, yeah, like a camera. It is, the original camera. We got a hole to let light in that can adjust the amount of light going in. You got a lens that you can adjust that can change the focus. As you get older, that lens doesn't work as well. That's why you'll see the people will show me code and they'll be moving crap. And I'm like, oh, good God, stop moving your code. Let me look. And I'll be like, okay. It takes me a while to get my eyes to focus now. It's really freaky now that I've gotten, when I got about 35, this started happening. It's very annoying. And here's the thing, this thing, so light comes in, it focuses approximately here for the most part, but it hits the entire area. But for the most part, it goes down here. And we will also see, I'm assuming you guys can see my mouse pointer. Tell me if you don't, but I'm assuming you see my mouse pointer. And the fact that is, if that mouse pointer is being shown on Zoom, everyone sees my mouse pointer, whether I do anything at all. No matter what I say, no matter if I tell you not to look at the mouse pointer, if you're looking at the screen, you are looking at the mouse pointer. That's actually something you can't stop. You can force your eyes to not look at something, but we'll see why it's so slap in the face obvious for you in a second. So light comes in, it refocuses through here. It predominantly focuses right here in what's called the fovea. Well, it won't be a quiz on the actual terms, but the fovea is a useful term. This entire thing is your retina. So you have, and then eventually you'll get neurons here that all connect, meet up, and shoot down the back of your eye. There is actually a giant blind spot right here. Most of you probably know that, but just to be on the safe side, that's why you definitely don't have cameras in your eyes. You can't see a large patch of your eye, of what you're looking at in the world, and you don't know. I'll get full disclosure here. I was on medication for my eyes for 5 years, 6 years, because they did a visual field test for me and I had some weird blind spots. And they're like, what the heck's that? And then they kept on doing visual field tests. And at some point in time, it increased, they thought. Turns out, if you don't have coffee that day and you're tired, it increases your blind spot, or the tests go off. But they didn't take that into account. They put me on drugs for my eyes for 5 years, thinking I had early onset regular pressure glaucoma, because I got weird blind spots in my eyes, and I'm blissfully unaware of them. I don't see parts of my visual field I don't see at all, and I filled in the blanks. And you've done the same thing. Every one of you fill in the blanks. What you're seeing here, you're not actually seeing. You're piecing together very, very quickly using your brain. So you don't have little cameras in your head. You were piecing things together. And so when the first digital camera came out, they gave it to a grad student to figure out computer vision as like a summer project. And they're still trying to figure it out now, right? No, they gave it to them in the 60s. Now figure out computer vision, like the arrogance of humanity on this one, right? Most of the heavy lifting is not done here. It's done here, which we'll get to in a second. So neurons, get light, shoot down the back of your eye, and go back here to the occipital lobes, the bumpy stuff in the back of your head. My back of my head, everyone in my family has this weird, ugly looking back of our heads. It's really not. It's not good. Anyways, but that's where all the visual processing is done. It goes back there, goes right here, and then starts processing on the way up the back of your head. So it also does a crossover so that both eyes, the visual processing for both eyes, go to both sides of your occipital lobe. So they cross over the superior colliculus. Yes, I had to memorize all of these different things, but I don't remember half of them now. Measure of Gudden, like, my God. But it's essentially crossing over and going to the back of your head here, where you do all your processing. So light comes in, it gets focused by the retina, it hits here, it hits this spongy bunch of epithelial cells, this bunch of cells at the back of your eye, which just bounce the light off. And then you have a whole bunch of receptors, neurons essentially, but they're rods and cones, just waiting for it. They're photosensitive, they're light sensitive neurons. Just at the back. So when the light hits there, these things fire off. So if they get a light, they go, hey, I'm on. Okay. And they fire. They get excited and they send off a signal. Those signals then get combined in weird, wonderful ways, which we'll get to in a second, to these cells over here. So there's a bunch of little basic signal processing down to here. And then the wires just back to the back of your head. The cones that you have here, this is what makes us special, actually. It makes us very special compared to a lot of other mammals, not other primates, but other mammals in the most part. The rods are the things that are seeing light and dark, and the cones are the things that are seeing color. They're little midgety things, and they're different cones for different colors. 3 different cones for 3 different colors, which is why our light for like television and for our monitors and everything else use those same damn cones. How we see is how we represent our world as well, how we break down the world. That's how television signals were being sent around. This actually is a pattern for what your cone, the grid of cone cells in the back of your eyes look like. What you can't see very well, there's little blue dots right around here. There's a whole bunch of red dots and there's a whole bunch of green dots. But those little blue dots in the back there, there's a reason why you can't see them, because you don't have very many of them. You're not actually that sensitive to blue. Some of you may not be sensitive to blue at all. I don't want to be making presumptions here, but there's little blue dots in here that are hard to see. So those are sensitive to blue. There are some cones that are sensitive to green. There's some cones that are sensitive to red. And for 5% of the male population, they're missing one of those red or greens. They're either not working that well or they're not working at all. That'll give you red-green color blindness. It's 5% of the male population. It is a huge number of people. It's sex-linked. That's why it's mostly men that have it. But still, it is. They're missing half of what you see for color. They're still seeing the world. They're just missing some of the color aspects. Here's what we actually get. This cone, the blue cones, are receptive to about 420 nanometer wavelength light. So that's the blue, the violets. Your green cones are for 534, Your red cones are for 564, and your rods, the thing that are detecting light and dark, at 498. They have a pretty wide distribution of what will set it off. So if you get a light at that frequency, boom, it goes off every time. If you get a light at a higher frequency, it doesn't go off as often, goes off some of the times, not all the time. If we're down here, goes off some of the time. Well, we have 120 million rods and 5 to 6 million cones. Our cones, 64% of them are red sensitive, 32% of them are green sensitive. That's just all up in this range here. And 2% are blue sensitive down here. So the vast majority of your color encoding, the things you see in the world in terms of color, in terms of hue, are based off of red and green. That's what we're really good at detecting, red and green. And if you look at colors, even when we have blue, the way you differentiate your different blues is the amount of red and green that's thrown in there as well. So red and green we're really sensitive to. By the way, this is RGB or RGB color mapping. If you'd ever do anything with, Photoshop, for example, you'll get a red, green, blue color thing to determine your color, RGB. But we're really sensitive to red. We're pretty sensitive to green. Not so sensitive to blue. Okay, 2% of your cones. But we got a lot of rods. So that's why luminance, brightness is extremely effective. That's what we're good at. You may not realize it. We think we're really good at seeing color. We're not. We're really good at seeing shapes and brightness and darkness. 120 million of the damn things. But your cones, oh, wait, that's why we're sensitive to red. That's why it's a lucky color, traditionally, at least in China. That's why it's a color of warning in North America, because it's so sensitive. We're so good at picking it up, it pops. So either you use it for a warning or you use it for like, yay, it's happy, it's fun. But you use it because we're so good at detecting it, unless you're red-green colorblind. So I have a friend who was actually a visual designer at CD Depco, red-green colorblind, cannot pick strawberries. It's just guesswork. He's feeling around, he sees something, he knows it's a strawberry, he picks it and he hopes it's ripe. He has no idea, and he can't see it in the patch. Here's the weird thing. So I want you to do an experiment. I can't see you do the experiment, but I want you to do the experiment. I want you to hold up your finger and look at it. Okay, what can you see? Well, if you're like me, you don't see much because glasses are always muddy and dirty and have scratches on them. But you could see, or hold up a pen. Look at the tip of the pen. How much can you see? Okay. So now move to the side. At what point in time do you not see it anymore? You probably see it, but how much detail do you see? Or how well do you see it? At this point in time, around here, up to the side, but flat to me, I still sort of see my fist, but not much. It's still there. I see something. If I move it, I still see it. But if I move it in front of my eyes, I see it extreme detail. It just suddenly, we got this one little part here. So the size of our pixels, essentially, my visual pixels in my eye, are extremely different. Look at this blurry, barely see anything at all, like large scale of here. But where my fovea is, that one part of the back of my eye that's really sensitive, where all my cones are, is extremely good. So we can resolve, at least undergraduates when they do the testing at least, can resolve 100 points on the head of a pin held at arm's length at the center of your fovea. It's extremely good. And just a little bit outside of that, the parafovea range is 50% of your visual processing on this little tiny patch in the back of your eye. The vast majority of your eye is doing this large scale stuff. The back of your eye is this really intense pinpoint window into the world, which is insane, but that's what it is. So what we end up having is this particular thing where with my two overlapping eyes and I'm pointing it at one thing, I see something in extreme clarity and the rest of it looks like crap. I get effectively this kind of very, very limited range. I can see up to actually 110 degrees outside behind me, almost like a deer. Uh, and this is what I get. I'm looking at 24.5 in extreme detail. I can see exactly how bad the font is here. And yet up here, I'm not seeing squat. I see blurry stuff with this B, right? The flowers all around it, probably didn't even notice that at first because I went right to the B. The flowers all the way around it are blurry, and as it gets closer to where my fovea is, I get this extreme detail to the point that if I'm looking at the bee, I can see the exact translucence of the wing and any kind of pattern on the wing. And yet if I'm looking at a picture like this, I can barely see I can barely see the flower at all. So this is my central focus is the bee normally, and the rest of this stuff. And as soon as I leave that focus, now look at the clarity of the flower. This has effects though. This is the original Boston subway map. Ottawa doesn't have a good subway map, so I couldn't even change this if I wanted to. And the train doesn't actually come at all, or on time. I was like, here it comes when the O train was being released, was opening up because I know how hard it is to run those things. So this is the original Boston subway map. If you're running to catch your train, you're running to get your subway, you are not staring at this for a long period of time, or you want to glance at things. You get, so this is Kendall, MIT. That's actually where MIT is located. It's in, it's in, uh, it's in Cambridge right here. Harvard's up here. MIT's right here. So all, the brainy smart people are around here. Google ends up being right here as well. That's where the subway stop where Google is. And Ruggles and Northeastern is here. That's where my old university was. Okay, this would be my line. That's what I did every single day. Now, if you are quickly glancing at this thing, you get the following. I see Kendall, MIT. Everything else is a blur. This is called a mongrel. It is, if I stare at one point, what the low-level pattern recognition I get. They can actually do the experiments on this. What low-level pattern recognition I get for the rest of the scene. I get clarity right here, and everything else is just garbage. Not garbage. You get some impression, but it's not really good. And so what you really want is, instead of this, you want to redesign your subway maps so that when you get a quick view of this, I don't need accuracy of where the lines are. I don't need this kind of whirly-do thing here. I just want the lines, because it doesn't matter where it's getting off. I'm going to a destination. I want to see the line. I want to see where it goes, but I don't need to see the exact turns and stuff like that. So I want to get straight lines. So I don't need this little elbow thing in here. That is actually what the line does, but I don't need to see it. I want a straight line. So boom, straight down. And what I'm trying to do is get straight lines so that when I look at the mongrel, I get a better, cleaner view of the map. So when I'm running, I go, there, go. Because people are looking at this quickly. They're not staring at it. They're not still reading all the parts, but they just want a quick, immediate response. This is just one use of why we need to know about this. So how do we end up seeing? If we are so terrible at seeing things, what happens? Well, that's kind of creepy, but we move our eyes. This is someone looking, doing an eye gaze experiment, but it could be anything. Your eye moves. If you see someone read, try it out at some point. Now, your eyes just zipping around. Even when you're just looking around at the world, your eyes zipping around. You have these little quick movement. This is Michelle Borkin, the person who designed the slides originally, and then I modified severely, looking at a chart. She has an eye tracker, infrared camera checking her eyes, seeing where her eyes are, so it doesn't blind you. We have a visualization display, the thing you're looking at. We have an eye tracking computer, so it's running the eye tracker, and we have an experimental computer. And she wanted to see what people are looking at when they look at a book. So what did you look at when you saw this picture? Your eye made a particular pattern. Not all eyes were going to make the exact same pattern, but they make a particular pattern. This is what graphic designers obsess over and what we're going to obsess over to a certain extent as well. That immediate, I'm looking at that thing right there, is what we want. We need something that just draws your eyes on how fast you go and how you process this thing. Because if we're learning anything for this entire course, it is pushing data on the screen is easy. Controlling how people see things to make it maximize their ability to use that data, that's hard. So you can put 40 different visualizations on the screen. You can't expect people to see it. To the point that I still have this problem. I'm redesigning. If you didn't notice, I think I just did it for you guys too. There's options I found out about for CU Learn, allowing you to collapse and expand different topic sections. No one told me about it. No one showed it to me. Like it was one of those hidden things you had to find out in the end. Because students were complaining, it's just all the text was there, and I couldn't figure out a way to get rid of and collapse down some of the topic areas. You had to do some extra stuff. Because what we want is, this is the topic I'm looking at right now. That's the thing I need my eyes on. Everything else should be hidden away. You're designing for how people see. So how do people see? First thing, they jump to the center. They jump around a little tiny bit, just enough to get a view of things. They jump to the title. Or at least Michelle did. Quick read of the title. Notice it's on the next line. Boom, jumps to center, jumps to the first bar chart. Holy Bible, reads the title. Jumps to the center, jumps to the next one. Jumps to the next title, jumps to the next one, jumps to the next one, jumps to the next one. People will, I don't think the Diary of Anne Frank, she didn't even read it. She just, done, good enough, that's the last one, right? But you went to the bar chart, the big black, large bar chart first and looked at it. And then you can look at the scales afterwards. And this is being done in like a second. That's how you read. Oh, and there's bar chart. Oh, and now Diary of Van Frank. Forgot that she did do that. So eyes are moving extremely fast. They're designed to actually handle this fast movement. Your brain compensates for it. The fact that you have two different views and you merge them together, your brain's also doing that. It's all processed back here. In your actual eye, you get something also weird. And I like pointing this out. And this is the reason why I wore this particular shirt. What color is my shirt? I'll actually leave it open because I like forcing you guys to wake up every once in a while. What color is my shirt? Except it's not. It's technically white. Yeah. With a very, very, very light blue stripe all the way around, like a checker pattern all the way around. And even wearing the damn thing, I look at them, it's blue. And then I go look closer. No, it's actually white with a bunch of blue little checker pattern in it. Because the blue is so light that it blends with the white. I don't get the lightness to darkness difference. My blue cones are getting set off, even if you're right up next to it. By the way, I'm going to be doing this for all my clothes for the set perception things. I always have an outfit that works with perception. Even if you're really close up to it, you would still, unless you're really close to it, you push it out at all, it looks blue because you're not seeing the edge. You're not seeing the edge because of this. The center surround, this is how our rods and cones are actually working. We have a cone here, we have a cone here, we have a cone here. So let's say we only have 3 cones, but it's actually all the way around. It's just a grid of cones. If I have darkness on one side, so one of the neurons, this one here, is getting darkness, this one here is getting darkness, and the one in the center is getting lightness. The neuron in the center goes, holy crap, activate, and gets really excited. Because what we have here is this rod here inhibits this one, and this rod here inhibits this one. Essentially, your friends are preventing you from doing something, getting too excited or doing something stupid. It's all the people around you are keeping you down. They're suppressing. So when they are excited, you get less excited. They prevent you from when they're excited, you get less excited. This first neuron is still firing, but because of this inhibition, this bipolar cell, this cell here, doesn't get much of a signal. It suppresses what this thing has a bunch of stuff happening, and these are suppressing how strong the signal is. If this is off, there's no lightness, then they're not suppressing it anymore. And I get a big, strong signal. But when they're all on, they're suppressing this thing. If this is off and these are on, not only is this barely firing, but it's being suppressed by the nearby neuron. So you get no signal. You get complete inhibition. And if I have all dark, well, it's not preventing things, but this is also not firing. So natural state, no light at all, I get this. But as soon as I get lightness on the other side, it's suppressing it down to this. So go from here to here when the nearby neighbors have some light. And if I have light in the center, but not on the nearby areas, I get extremely excited. Nothing's suppressing my signal. And if I have all light, I have only a slight activation because I have some suppression and the neurons firing, which allows us to detect edges. We'll do other processing on top of that, but we get an edge detector, which gives us this. Don't throw up or something like that from this thing. I find this very disturbing. We have a white circle in the center, gray edges all around, and a black big square at the center. And if you look at the center, one of these dots, you'll the periphery, the thing that's creeping you out, the periphery circles have a big black, like a black blob in the center, despite the fact that they're white. And as soon as you look at them, they're no longer white. They're white. They're no longer with a black blob in the center. And here's what's happening. On the gray bar here, I have some inhibition around it, but I have no inhibition above and below. In the center point, I have inhibition here, 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 here. I have more inhibition because the up and down are also inhibiting. So in low fidelity or low resolution areas, I get a lot of inhibition in that center point. So when it's often my periphery. And as a result, that blob looks, you should get, so this is inhibiting this centerpiece. So this should be, this dot here is less bright as a result than compared to the gray below, just a normal gray bar in there, which has less inhibition. So what ends up happening is I get a Hermann grid where I get these black dots in the center of the circle because of how my cones and rods are working. And you get weird visual effects. Other nicety about all this, though, is this. It's nothing special. It's just a bar. It's well, it's not even a bar chart. It's what the heck is it called? It's a pointed bar chart, but yeah, it's a stacked bar chart. And I'm not going to give it a name. The point I want to bring up is, did I need to put a black barrier around the blue, around each of these things? That's why graphic designers hate, you know, outlines and stuff like that. I always used to put outlines on everything, and they're no, take away the outlines. Notice the yellow doesn't stand out as much though, because it's close to the white. They're both bright, and I don't actually see it pop out quite as much, or the shape of it's not as obvious. The blue is. But notice I don't need an outline because I have light to dark, and any of those times when I have a light to dark change, it shows up, which means I don't need this. I don't need a big black box around each of my bars because the bar itself, separates itself from the background. If the background was the same color as this, I would need a black bar around it, right? If I had an orange background or it was like gray, I would need a black bar around it to show that the edge, where that edge is. But if I don't need that, white space works just fine. I parse things based off of the difference, not the color, not the actual color and the lines don't make a difference. It's the differences that make the difference. So let's do some quick low-level feature processing. So this is our brain. This is where everything's going. And this at the very back, where as soon as it comes off the optic nerve, at the back, first level visual processing, I get shape, very, 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 very basic shapes, blobby shapes. I get color, and I get motion. That's why you cannot not see this. When I move my mouse, your eye goes there because your brain is predisposed to try and track it because they could eat you, right? The mouse won't actually, the mouse cursor won't actually eat you, but your brain is just hardwired for like, motion's the thing to watch out for, right? The plant's not going to eat you. The thing that's moving around in the plants, where the little rustle of plants over there, that could. Or maybe I'm trying to track a deer, and oh, that thing that's rustling over there, that might be food, or it might be something for that might eat me, right? You're predisposed for that. By the way, notice what when we're really good at color, right? Why are we looking at red? I skimmed over this because we're going to hit color perception later, and we're going to remind you. But why is red so important? There's a reason for it. And I'll say primates have red, like really, really good attention to red. Most other animals don't. Most other mammals, I should say. Why red? Seems weird. No one wants to answer. No one wants to take a shot at this one because it's a weird thing. Why red? Like, there's not that much red grass, right? What? You're if you're going to eat a deer, it's not red. So why do you want to see red? And this is all conjecture, by the way. Yeah, pretty much berries. Berries, fruit, anything that you're going to eat, if it's ripe and it's a fruit, it's red, oftentimes. And it stands out. So it's the thing that's edible from a plant oftentimes is red. That's what I want to eat if I'm in a tree. But what warning color, I mean, in nature, what warning color we have? It's not a recent evolution. Oh, blood. That's an interesting. I never thought about blood, actually. That actually would be, but you would think other animals would also have that as well, right? They don't want to die either. A deer would be like, hey, what the hell is that thing, right? They sort of know that if they're bleeding or not. So you would blood of an animal perhaps to see if you got the thing you killed. But tigers don't have very good red eyesight, right? They they chew on it. They know. Could be tracking though. That would be a great hypothesis. But there's some evolutionary advantage, whether it's berries or whether it's tracking blood stains and not having a good sense of smell. Our sense of smell sucks compared to the other mammals. Whatever the case is, it has some evolutionary advantage we were presuming for finding food. And that's why we're so good at it. And the reason it's for primates is because we'd be in a tree looking at fruit originally, and it's sort of held over for humans. But this is what ends up happening. When we have this, we get this. Find the red circle. How long did it take you? If I said find, there's other things that you can't do. But this is called the pop-out effect. It used to be called pre-attentive processing. There are certain things we see right away. And if you design your visualization system right, that's what you're looking for. This, oh, I know what that is, right? Find the red circle, find the red circle now. A bit harder, at least I find it a bit harder, but it's still pretty fast. To the point that find the red circle in this, if I tell you find the red circle before I change the slide, you will find it without scanning at all. Other times you have to do this like scan of the visual area. This thing just, there it is. You don't even have to look for it. It just slaps you in the face. Find the red circle. Find the red circle now. Now notice that you have to scan. You have to manually go through this thing until you find it. Other way, in case you're wondering, it's right here. Oh, wait. How did you know where I was looking? Motion. Pre-attentive. It pops out. No matter if you want to see it or not, you have to actively fight against it. As someone who is easily distracted, I don't want to say ADD, but easily distracted, right? This is one of the challenges you have with the world. There are things that call your attention, and people like using them, and people like me don't have an easy time tuning out all of that crap. Someone's having another conversation while I'm talking. I listen to it. I can't help it. If I see something move in my periphery, if you're watching a video while I'm teaching, my eyes are there. You're screwing up the lecture for everyone else because I'm like, what is he watching? there are certain things that are, that you need to be able to tune out, and that's you have to actively use cognitive processes to tune out these effects. By the way, this is why blinking HTML was so big in the 1990s. I don't know if you've ever seen it, but there was a big thing where everything was an animated GIF and everything had blinking HTML. So all the text was doing this sort of thing. Frustrating as hell. Called your attention. Oh, by the way, where else have you seen this? You've seen this kind of thing recently with ads, or maybe you may not have noticed it. Every once in a while, but it's a really bad dark pattern for web design. Anyone see those websites where like you go to a website and you'll see this like little shake, like uh, retirees in Florida have this winning strategy, and the thing just does this, just a little bit. Doesn't have to do much, just a little wiggle, and it's enough that every single person's eyes just go there, and you have to fight your eyes constantly to not go look at this damn thing. It's intentional on their part because they know you can't tune it out. All right, so we have pop out effect. We got a bunch of other ones, right? So we have hue, we have number estimation, we have density and contrast. There's a dense area, right? Curvature, there's one thing curved here. We have closure, whether something is closed. We have some, there it is. Boom. We have size or width in this case. We have length, which is orientation. We have length, this one right here. You're way faster at finding those things than you would if you had to manually scan through this. But here's the kicker. Or I have all these other ones as well. There's a million and one of these things that you can use. They're very useful to look at, by the way, or to consider. Luminance, boom. Light direction, boom. We're all about seeing the different thing. It's the safety mechanism for one thing, right? We're looking for the different, and some things are really good at finding that difference. And the key is, if I have multiple of these at once, what happens? And that's what I wanted to bring up earlier when we're looking at visualization designs. That if I am a human and I have a particular visual channel, so I have hue and position, let's say, fully separable, I can find the red circle on the right easily. Hue and size, harder. There's some interference. So find the big purple circle. It's right here, but I have to do a little bit of scanning. I have to work a little bit. Height and width, really hard to find the really big circle. And if I have red and green, they merge together like two different sounds. When they're close enough, they just become one note. Or two multiple sine waves, they become one note. Red and green, or multiple colors, for example, together. I can't separate them, and I don't get a pop-out effect anymore. I cannot find the red circle here because there might be a purple circle in there. It doesn't, like if there's a whole bunch of different colors there, it's hard to discriminate that or find all the things that have a high red component, right? So some of them are purple, some of them are red, but I can't distinguish those. And so my job as a designer is to find the right amount of separability to make the thing I want to call attention to pop. And if I don't do that, I get random weird stuff. I don't get what I don't do anyone any favors. By trying to push too much at once, I actually make it harder to see. So this is fully separable, red, green, blue, and yellow, really hard to separate. They're integrated. And so if I want to make a pop-out effect, I want to draw attention to a particular point, a particular thing, particular item. Its motion might be really good. Spatial grouping might be really good. Orientation helps. Of a particular elementary shape that we're looking for, I have, or hue. I love hue and lightness myself, personally. You get things like this. But just because, Super Bowl's coming up. This is the quarterback sneak, and the number of sneak attempts made by various players, and the success rate. Yeah, if you've ever watched the Patriots, because I'm living in Boston, if you ever watched the Patriots, you know Brady really loved the quarterback sneak. He still probably does it to this day. He also does little short plays and stuff like that. He's abnormal in many respects, but it pops, right? You know exactly what they're trying to point you to because they're using a different hue. Everything else mutes. You intentionally mute everything else, and the thing you need to call attention to, you maybe use color, maybe use a shape, maybe use something that people are looking for. It's how they also design furniture and decorate a house, right? You cannot call attention to everything. So you have mute all your colors and you have one thing that pops, one thing that calls attention to itself. With design, with visual design, same thing. We're just doing the same principle for visualizations. All right. I'm not going to get to a design exercise, but I want to get to this first. So they get it right in black and white. Maureen Stone is a very nice person. I've met her before. She's the person that designed the color palettes and stuff like that for Tableau. In case you're wondering, she is one of the world experts in color design for visualizations. That's what she does. She does color. Weird niche, but that's what she does. And her big thing is, if you're going to use color, you better make sure it works in black and white. So for any of your visualizations, you put it in black and white, print it on a black and white printer, or just make it black and white. See if you can read it, then put your color back in, or then check your colors, because your colors do something very different. We're going to look at that when we look at color again. In black and white, we see one thing. In color, we see something else. But it has to work from black and white because A, some people are colorblind. B, you see things differently in black and white than you do in color, and how you view the world will change. You actually see color difference, brightness, the lightness, contrast differences, how you read this map. And so you need to make sure that it's legible in black and white before you move on to color, because black and white carries a lot of component, but people just keep forgetting that part. So when we talk about luminance, I always want to say luminosity. It's probably not even a word, but I used it for years. Luminance, it is the amount of light that comes into the eye from a surface. So the brightness is the perceived lightness from a reflection. Brightness is from a emitted light. So this flashlight is bright. This is a light. This is a light color, right? This yellow is a light color. This yellow here is a light color, but this monitor that I'm looking at is bright. It's emitting light. It depends on how you want to look at things. Normally, lightness would be for paper, but we can talk about lightness here. Luminance is just, we're going to use it as a general term. How light to dark it is. I want to hit one thing first. So if I have something like a newspaper, I told you, everything is about the difference, we're not actually viewing the world, we're composing our world. Not only are we composing our world, everything that we see is all relative to the surrounding. So this O, this white space in the O, and this black piece of an S, if I remove the rest of, don't I have that? Oh, there it is. Thin gray is the top part of gloves. Okay, so this is that gray. This is that O. That O is this dark gray, and this, because I've removed the context, now you can see it by itself. We will see light, brightness, color in a constancy. So you put all yellow all around you and everything will look, you still see colors. And brightness. So in a dark room, it still looks bright or dark. It's how we've evolved so we can actually see the world in all these changing conditions. But it means that it's not, you can't just assume that I have this red, it's going to be seen. It's based off of everything else around it. Okay, so if I was simultaneous contrast, this bar, by the way, is just one color. The gradient changes it. So if I have color gradients, it changes how I perceive things. I want to throw one more thing. Those boxes are the same. And the A and B colors are exactly the same color. That's the point. If you know how people see the world, you can design things correctly, but otherwise you can kind of get things wrong. It's all about the relative, how it relates to the rest of the environment, what colors you choose, what lines you use. Everything is based off of the relative area that you're looking. It's not universal. You don't have cameras in your head. Green is not green. Blue is not blue. It depends on what it's next to. That's what we're going to pick up next time around. So I'm going to leave it there. We're going to go find some optical illusions next time around. So think of your favorite optical illusion. When we come back, I'm going to have a quick snack here. When we come back for the lab, we're going to be looking at D3. I'm going to do a brief overview of what we're talking about. I was going to have you look at the lab exercise. It's in the other, we have a lab See Learn course, which I think has one thing in it. It's pretty much just to show that like a couple of these lab things. But I didn't want to just necessarily just give away answers to the homework, but I don't want you panicking about D3 or programming because I know it can panic some of you. So I wanted something I'm hoping is a nice little way to get your feet wet, to get the answers to the solution for the lab so you can see what I did versus what you did and get a bit of exposure before you dive into any D3 coding rather than just hitting a homework. It's going to be like hitting a wall. Because I want you to feel comfortable with it. I'm okay with helping you guys a lot on the D3 homework. I need to have a checkbox and say like, yeah, I showed them D3. I showed them how to use it. I don't need to say that they're experts in things. I just need to say that you have been exposed to it. So that's what this lab is all about. It's to help you with the homework and teach you somewhat about D3. And that's what we're going to pick up in about 5 to 10 minutes time. Okay, I'll see you guys soon for the lab. Actually, I'm going to, do you want me to, I'm going to stop, I'm going to leave the meeting open. I'm just going to mute myself, turn off the camera and stop the recording. All right, thanks.